talk. Okay, the next talk is by Niccolo Beltri. The talk is about type-theoretic construction of the final coalgebra of the finite powerset functor. Please, Niccolo, you can share your.
Can you see the slides? Can you hear me?
Yes, we can.
Okay, perfect. So indeed, I'm going to talk about various constructions of the final powerset functor and its final coalgebra in constructive type theory. And my motivation here comes from the semantics of non-deterministic systems. So the final powerset functor, which is a very simple mathematical construct, if you wish, since delivering the set of finite subset of a given set. So it's very simple, but it's also very, very central in the study of the behavior of the non-deterministic systems. And here I'm thinking about stuff like process calculi and NFAs. Because, for example, a finitely non-deterministic system is determined by a coalgebra, which is a function of this type here. From a set of states S to the set of P fin S, which is here the set of finite subsets of S. So, and the way to read this is that the function C associates to each state X in S the set of new states that are reachable from X. So, in other ways, in other words, is a functional way of expressing the transitional relation of an unlabeled transition system. And it's not easy, it's not difficult, sorry, to modify, for example, the return type here to accommodate also labels and other and also other form of non-deterministic systems, for example, still using Pfin. Okay, and the behavior now of a non-deterministic system, now starting from a given initial state, x0, is fully captured by the finite coalgebra of Pfin. And now what are elements of this finite coalgebra? These are execution traces that can be obtained by running the coalgebra C on the initial state iteratively. And the resulting traces are infinite trees, they are possibly infinite trees, and the order of these trees is finite and unordered, the branching. And so in the literature, there exist many concrete constructions of the finite coalgebra of Pfin, and more generally of other finite powerset functors. Here I included some of the authors that worked on this problem, but there are many others. And so it's a well-studied problem in category theory. But all these constructions take place in set theory, and the reasoning is based on classical logic. While my goal would be to study to develop formalization of semantics of non-deterministic systems in proof of system that are based on intuitionistic type theory, such as Agda or Koch. So I'm interested in, for this aim, I'm interested into investigating representation of the finite powerset functor in a constructive setting and how its finite coalgebra can be constructed. So, and this will be basically the construction I'm going to show you during the talk. So this the paper stemmed from a formalization in Cubical Agda, which is a variant of Agda, which is implementing cubical type theory, which is a particular syntax for particularly well-behaved syntax for homotopy type theory. And you can find the full formalization at my GitHub page. And in the talk and in the paper, will be divided into 3 parts, corresponding to 3 different approaches for constructing this finite coalgebra, and also for representing the finite powerset functor. So I'll be discussing a construction using setoids, also known as bishop sets. Then I'll move towards maybe, if you wish, more univalent mathematics, univalent foundations, using shared construction using higher inductive types. And then finally, I will be analyzing a famous construction by James Worrell that is done in set theory and try to port it in in our constructive setting, and this is a construction as an omega plus omega limit. Okay, so let's see the first construction using setoids. So what is a setoid? So a setoid is a pair of a type together with an equivalence relation on the type. So these are constructs that are usually employed in intuitionistic type theory, where whenever there is no notion of a quotient type. So now the way to read the set of AR is that now R is the notion of equality on element of A, and then amorphism between two setoids is now a function between the carriers A and B that respects the relations. So it sends the related elements in the input to related elements in the output. And one can define the finite power set in this setting. So given a setoid, you can construct a new setoid containing finite subsets of the original setoid. And now the carrier here would be lists of A. This is the inductive type of lists. And now the relation on lists would be this list bar R, which is spelled out here. And I'll just briefly give the intuition about this relation. So it says that two lists S and T are related whenever, for any elements of the first list, there exists an element of the second list that is related to that. And now here is the same thing, but now starting from the second list, T. So two lists are related here if they have the same, they contain related elements. So for each element in the first list, there is a related element in the second list. Now, this list bar here is usually called, is a particular relation lifting for the list functor. And it's also called a relator usually in the literature. And using this definition of the finite power set as a setoid, one can construct the finite coalgebra in the category of setoids as follows. So the carrier will be the type of trees, tree, which is the finite coalgebra of the list functor, and the relation. So two trees will be related. The equivalence relation here will be 3R, which is the kind of conductive closure of list bar of the relation lifting. And so just to give a flavor of how these things look in Agda. So in Agda, you can define tree as a coinductive type or a coinductive record where there is one destructor. So given a tree, you can destruct it or make an observation on it, and the observation will give you a list of the subtrees. And now the relation 3R will be defined between two trees is the relation that relates all the subtrees of both trees with this list bar of 3R again. So it's kind of a conductive closure of 3R. And now again, in here you say that two trees are related whenever for each subtree of one tree there exists a subtree of the other tree, and the two are again related by the 3R relation. Okay, so this is how you will do things using setoids, but but this is not really in the spirit, for example, of a homotopy type theory, where the notion of equality is really the identity type of so not an ad hoc equality given for each type, but the notion of the equality type. So we'll move in this direction. So in fact, actually, in homotopy type theory, it's possible to define the finite Powerset functor as a type, not as a setoid, and this can be done using higher inductive types. So higher inductive type is like an inductive type, but one can not only have generators of constructors for the point of the type, but that one can also specify constructors for the equality elements of the equality type or higher equality types of the type you're defining. So, for example, this is one possible way of defining. So let me say also that these higher inductive types, or HITs for short, are usually employed for the encoding of geometric spaces in homotopy type theory, like the circle or the torus. But they can also be used in a more mundane way, if you wish, for the specification of term algebra of equational theories. And this is the way we use them, because it's possible to specify the finite power set, so the P-fin A, so the type of finite subset of A, as the free joint semilattice on the type A. So in particular, one can just take the equational theory of joint semilattices and write down basically higher inductive types, which has the constructors given by the theory. So more concretely, we can see here that this is how one can define P-A. So it has three constructors. So there's the empty subset and 3-point constructors, if you wish. So the empty subset, the singleton subset, embedding A into P-A, and the binary union. And then there are four constructors for the equality type, which correspond to the equations that one imposes on the theory of joint semilattices. So associativity, commutativity, and idempotency of binary union, and then unitality of the union with respect to the empty subset. And then there is also another constructor that we're not going to look that much into the details here, but it just says that any two identifications, so any two elements of the equality type x equal y are equal. So it just says that there is no interesting higher structure here. In homotopy theory, you will say this is a set. P-A is a set or an H set. And but equivalently, one could also define P-A maybe even more directly as a quotient. So by quotienting list A by this relation, so this again is the relator applied to the equality type. And so again, so this relation relates to lists whenever they have the same element. So if they are equal as finite subsets, really. So this is kind of a very, very intuitive definition. But so as it is well known, in multi-loop type theory, or it doesn't have quotient types. So then this can be encoded only in kind of extensions of that. For example, using hits. So if you have hits, you also have quotients, and this can be defined as a hit. So these are both definitions that use hits, and they are actually equivalent. And so in Cubical Agda, just to give a flavor of how things are defined, one can specify P-A in the following way. So this is basically this is the same way as you will use the same syntax of inductive types, right? So in here, this will be exactly the same constructors that you have in any inductive type, but then you have this constructors for equality type, and you will really write down the same, basically what you have here is really the same thing. And then you have this extra constructor which correspond to this here. Just wrote down in a very short way what that correspond to. So, and I don't have time to really talk about Cubical Agda here and its features, but the only thing I would like to mention is that this equality type here is not really the inductive equality type of intuitionistic type theory. So the one with only one constructor, which is given by reflexivity. So this is something else. It's a kind of primitive. It's something that comes from the geometric interpretation of a homotopy type theory or cubical type theory. So intuitively, an identification of x and y is basically a function from a certain interval type to A. So cubical type theory or Cubical Agda also comes with the primitive interval type I, which is a kind of synthetic representation of the. You can think of it as a synthetic representation of the unit interval of real numbers between 0 and 1. So, and in this, and now, yeah, identifications are basically, you can think of them as paths between points x and y. So each type is interpreted. Can think of it as a particular geometric space, and now an identification of this form is a path for an interpretation of x and y in the model. So there is kind of some analogy here, if you wish, with paths in geometric spaces which are functions from the interval, particular functions from the interval. And in particular, so if you think of this encoding of the equality type, you'll see here that now these are again kind of constructors which have return type P-A, because now these are kind of if you unfold the definition what I wrote here from the constructors, you see these are basically again functions from the interval, specific function from particular function from the interval type to P-A. So this is kind of what's one of the requirements of inductive type in Agda is that all the return types are given by in the constructor that the type you're defining, and in some sense here it's still present, this restriction. And now using this definition of P fin A is also possible in Cubical Agda to specify this finite coalgebra. So, and how do you do it? Well, you can just do it as a coinductive type. Again, so this is the coinductive type associated to P fin. So for each element of of this type here, you can destruct, that is one destructor, and it's given by the finite subset of the subtrees. And right, so this is kind of, so this works well. It works and it's accepted. There's accepted definition in Cubical Agda, but I have to say this is kind of an experimental feature at the moment, because so it is not well known in the models of Cubical Agda and Cubical type theory what is the right interaction between coinductive types that use higher inductive types in the specification. So I mean this is deemed as by Cubical Agda as a strictly positive type, and because of how the quality type is implemented. But I think this requires some additional justification in the semantic side. A cool thing that you can do with this kind of data types in Cubical Agda is that you can prove something that you usually cannot prove with coinductive types in basic Agda, so not Cubical Agda, which is the coinduction principle. So you can prove that this is a theorem that dissimilarity and equality are equivalent. So in particular, you have a proof term of the following type that given. So you can define again a coinductive notion of bisimilarity between trees of this type, and then you can prove that two trees are bisimilar, then they're equal. If they're bisimilar, then they're equal, which is something that you can do because of the way equality type is implemented in Cubical Agda. And so there is also another possible way of another possible candidate for the finite coalgebra, which is of P fin, again as a type, which is by considering this quotient. So remember we saw that the pair 3 and 3R gives the finite coalgebra in the category of setoids, but what about if you go back to types or sets in the sense of homotopy type theory? So is this the finite coalgebra there? So one can prove that this type is a fixed point for P fin, so the following equivalence or isomorphism types hold, but things don't work very well, as expected at least, when one tries to show that this type is the finite coalgebra of P fin. Because whenever you try, the proof of finality seems to require the full axiom of choice. So here is why. So you would like to have the following a proof term of this type. So given a coalgebra, P fin coalgebra on X, then you want to have a function from X to this type. But so then if you remember, we can define P fin X, for example, as a quotient of lists, right? So this is just one possible way of defining P fin. But what we can actually construct is something that is similar but not exactly the same. So we can construct a function from X to this quotient here, but starting from not from a coalgebra for P fin, but from a quotient of coalgebras of the list functor. Now the two functions here are related by this relation here. Whenever for every small x in the input here, small x in it, the two functions are related on when applied to the input are related by this relation here. So this is kind of a pointwise lifting of the relation, this relation to functions. And but then so you can construct something of this type, but then you will have to go back. So you will have to have an equivalence between these two things. You can always construct the functions from the right type to the left type, but the existence of a section for this type for this function seems to require it requires the axiom of choice, the full axiom of choice, because X is a general type. So if X were kind of a finite type in some sense, then you will be able to do this, but X is a general type and you cannot do this. Okay, so this type is also in some sense the finite coalgebra of P fin, but only assuming the full axiom of choice. And finally, I would like to discuss a bit the construction of a construction by Worrell in my constructive setting. So right, so Worrell, this is basically as I first discussed Worrell's construction. So what did you do? So first it took the limit of the following omega chain. So which is how you generally define finite coalgebras of, for example, polynomial functor. So you can always define finite coalgebra of a polynomial functor as a inset, as an omega limit of a chain like this. So what you take the unit type, for example, and apply and bang here is the unique map into the unit type, and then you create a chain by applying pfin to this iteratively to this map. You hold the limit v omega, and now so by the universal property of v omega being a limit, you know that there exists a function of this type. So there is an algebra structure on v omega, but it is well known that this is not surjective, and the reason why is that so now this map as by construction only maps into you can see elements of this type as trees, and this function only maps as in the image of this function only consists of trees which are finite branching at the top level. But you can construct counterexample to elements of this type which don't have this property. So, for example, there are in the limit there are sequences of trees of finite trees like this of this form, in which the branching at the top level is increasing indefinitely. And so this tells us that v omega, now the limit of this omega chain here, is so represents novel founded trees, but generally these trees do not have finite branching. So and the idea of Worrell is, of course, then okay, well, you should try to cut down this to only consider trees which have finite branching at all levels. And one concrete way to do it is by taking another limit. So now starting with this alg v omega, right? From v omega and this alg v omega, and you iteratively apply pfin on this function, you'll have another omega chain, and you take the limit. You call this v omega plus omega. And now you can Worrell showed that in classical set theory, now this function is injective, and so in particular v omega plus omega is equivalent to the intersection of all this of all the elements of the chain, and you can also prove that pfin preserves intersections, and in particular countable intersections in set theory. And so one has a chain of equivalence of this form, which from these two properties, stating that v omega plus omega is a fixed point of pfin. And in particular, there is a coalgebra underlying this equivalence, so map from here to here, and it's possible to prove that this is final. Okay, so how are things in a constructive setting? So things are. So the idea is that the construction of Worrell cannot really be replicated fully constructively, because it implies some classical principles. So it's possible to show that the injectivity of alg v omega implies a classical principle known as less limited principle of omniscience, or LLPO for short, which is an instance of excluded middle. And this states that for any Boolean stream, and such that this statement here says that the Boolean stream has at most one position n which contains value true, then it's possible to prove that then it holds that either all the even position of A contains value false, or all the odd position of A contains value false. So you can see here that this is kind of an instance of a student middle. And so from the injectivity of alg v omega, it's possible to prove this. And the proof factors through some odd effect, which it's possible to recognize as a form of completeness of two-element subsets of v omega. And the second part of the proof, the implication from the completeness to LLPO, is a reformulation in our setting of a proof by Mandelker, in which he did in Bishop style constructive mathematics, where he proved that from the completeness of finite subset of real numbers, it's possible to derive LLPO. And so finally, so if you want to really replicate the construction of Worrell, then you necessarily need to assume LLPO, and you can prove that now algebra omega is injective if also countable choice also. From countable choice of LLPO, we can prove algebra omega, the injectivity of algebra omega, and then proving that P-fin preserves countable intersection requires also countable choice. But then assuming countable choice of LLPO, you're able to prove that V omega plus omega is a fixed point of P-fin and show that the resulting coalgebra is final. So it's possible to actually really do the same proof. But again, you need the countable choice and LLPO, and in particular, the injectivity of algebra omega. Remember, this implies LLPO, so it's inherently classical. Okay, so this concludes my talk, and I just want to say a few words about future work. So I would like to also, so this paper, the topic of this paper was, the focus of the paper was finite Powerset functor, but it would be interesting to consider also other finitary functors, which I think we should be able to implement to encode particular families of finitary functors using particular grammars for higher inductive types. Then, as I mentioned during the talk, one still needs to study constructions of coinductive types, employing hits in the models to properly justify one of our constructions. And finally, so going back to my motivation, to be nice to develop denotational semantics of languages with non-deterministic or concurrent behavior in Cubical Agda, and for example, doing something like the formalization of a fully abstract model of bicalculus. We have done already, me and Andrea Vezzosi, in Garda Cubical Agda, which is a particular form variant of Cubical Agda, which uses Garda recursive types and not the coinductive types, but it would be nice to do it with coinductive types in Cubical Agda. Okay, so this is everything I wanted to say.
Okay,
thank you very much for your attention.
Nicolo. You exceed a little bit the time, then we have time for one or two questions. There is a question by Mitchell. Nicolo, given a nice formalization as hit, can we infer fully constructive intuitionistic computational interpretation here? Can equivalences be used to translate the proof constructively?
I didn't understand very well. Maybe I can read. I cannot find the chat.
Okay. Right.
1 second. Okay. Yes. Yes. I think yes, because somehow the formulation of hits in Cubical Agda is as a nice computation interpretation. So I think this should be possible. Yes. But this really depends on the way hits are defined. So yes.
Okay, let's move to Paul. Paul, can you unmute yourself, please?
Hello, can you hear me?
Yes.
Hi, I just wondered, I mean, you said finite tree. I mean, would it not work if you had countable instead of, countable power set instead of finite? Because it looked, for example, the first part with the trees, I mean, you could have countably branching trees. I would have thought it might, perhaps it would still work.
Yeah, so I think so which part of the
every point at which things worked, like both the part where you worked with setoids and the part where you had this hit defining P-fin, each of those I would have thought you could have a countable version.
Right. So that's true. So you can have that. We have, for example, also, yeah, you can define the countable power set on A as a hit as well. Yeah, you can. This is just the free omega join semilattice.
Right.
You can define that. Maybe what changes a bit here is the following. Maybe like so. Can you still see the slides? Yes, hopefully yes.
Yes.
So we have also this construction as a quotient here of trees by the quotient by this 3R relation. And so, okay, I said that in here things go wrong because you need the axiom of choice, and things will go wrong in the same way also for the countable power set, but something goes wrong even earlier for the countable power set, which I think already for proving that this is a fixed point, you will need the countable choice.
Okay.
Thorsten, excuse me, but I have to put your question. You can move to the crowd, any section to discuss.